Hello, my name is Özlem Deveci, and today I'm presenting my research project on Boundary-Supervised TransUNet. This presentation is going to be focused on critical application of deep learning and improving the segmentation of brain tumors in MRI scans with a specific focus on solving the problem of inaccurate boundary delineation. The motivation for this work is strictly clinical. Gliomas are aggressive tumors with median survival rate of only 15 months. Radiologists rely on MRI for diagnosis, but manual segmentation is slow and has a high error rate. That is up to 20% variability between doctors. Current automated solutions like the standard UNet face a technical gap. While they are good at finding large regions, they struggle with two things. The first one being small, low contrast regions, specifically the enhancing tumor. The second one being global context. Because standard CNNs have a limited field of view. Before diving into the model, let's look at the data. We utilized the BRATIES 2021 benchmark dataset, which is unique because it provides for distinct MRI modalities for each patient volume. T1 and T1 method provides clear anatomical structure with high brain tissue contrast. T1C, T1 mid contrast, highlighted actively enhancing the tumor regions after contrast injection. T2W, T2 weighted, shows fluid filled and abnormal tissue regions with bright intensities. FLAIR suppresses normal CSF fluid to make edema and infiltrative tumor areas more visible. Along with these four inputs, we have to target label mask that our model learns to predict each of these 3D volumes in massive with a spatial dimensions of 240 by 240 by 155 voxel or slices. We process these multimodal inputs to capture complementary features of the tumor anatomy. Data visualization segmentation masks. Here you can see the segmentation targets, the mask I'm training the model to predict. We classify every voxel into one of four classes. Class 0, healthy background tissue. Class 1, non-enhancing tumor. Class 2, edema, the swelling. And Class 3, the enhancing tumor. Now, I will discuss more proposed topic of research. The combining a hybrid architecture with boundary-aware supervision. The TransUNet architecture. I implemented the TransUNet architecture. This is the hybrid model that combines two powerful deep learning paradigms. On the left, we have CNN encoder based on UNet. These extras high resolution local features which are necessary for seeing fine textures. In the middle, I integrated transform module. Unlike CNNs, transformers use self-attention to model long-range dependencies. This allows the network to understand the global context. Essentially, understanding where the tumor is relative to the entire brain structure. However, a better architecture wasn't enough. The standard loss functions, like dice loss, treat all pixels equally. They don't care if the boundaries are slightly blurry. To fix this, I introduced a boundary-aware loss function. I combined dice and cross-entropy loss with a specific boundary loss term, which is weighted at gamma, which is at 0.1. This term acts as a differentiable surrogate for the BF1 metric. It explicitly penalizes the model when the predict boundary does not align with the ground truth margin, forcing the model sharpen its edges. For my experimental setup, I used the BRATIES 2021 dataset with a 70-30 training validation split. The implementation was done PyTorch on the NVIDIA Tesla P100 GPU with 16 GB of VRAM. I used the ADAM W optimizer with a learning rate of 0.0003. My primary evaluation metric was the dice coefficient calculated separately for enhancing the tumor core, and whole tumor. The results, loss curves. These graphs represent the training curves for both the simple loss combination, dice and cross entropy, and the extent combination that includes boundary loss. Although both training runs converge quickly, the two-loss setup typically shows lower overall loss values compared to the three-loss setup. This difference occurs because adding boundary loss in introduces an additional optimizing objective, increasing the total loss magnitude even when the model is improving. Despite the higher loss magnitude, the actual segmentation performance improved where it matters, looking at table 2. My model BS-TransUNet show on the bottom row achieved higher dice scores for the necrotic core 0.913 and the enhancing tumor 0.928 compared to this baseline. This confirms that the added supervision helped the model capture fine structural details that the baseline unit missed. Let's model the quality of the results. The left side, the ground truth label, the middle, the baseline prediction, and the right, my BS-TransUNet prediction. In this first example, notice the overall shape. The baseline model in the middle creates somewhat a blobby prediction, whereas my model on the right captures the nonce of the shape more accurately. In the second example, as we can see, the BS-TransUNet model produces sharper boundaries and significantly fewer false segmentations compared to the baseline model. In this example, most predictions from the baseline model appear similar, but with the BS-TransUNet, we can clearly see sharper edges and more refined boundaries in the region. Finally, in this example, observe the fine details at the periphery of the tumor. The baseline model smooths over these details, effectively ignoring the exact margin. The boundary-supervised model preserves these jagged edges, which is critical for surgical planning where every millimeter counts. To summarize the visual impact of my work, sharper boundaries, the addition of the boundary loss successfully eliminated the blur edges common in standard models. Consistency, we observed significantly less fragmentation and fewer false positives. The model produces segmentations that are more anatomically consistent with the ground truth. In conclusion, this project demonstrated the integrating explicit boundary supervision into a hybrid TransUNet architecture yields superior segmentation performance. I achieved this without increasing the model size, but rather by optimizing the training objective. For future work, I plan to validate these results using distance-based metrics like a Hausdorff distance. I aim to extend this architecture to full 3D volumetric prediction, currently slice by slice. I also want to explore adaptive weighting, where the model dynamically adjusts the importance of the boundary loss during training. This concludes my presentation. Thank you for attention.